All right, in this one, Black Holes Part 4, I want to talk about something called Hawking radiation. All right, and this is kind of wild stuff. This is the cutting edge of physics going on right now. If you're aware of physics, there was a guy named Stephen Hawking. He's a physicist. He grew up in the 70s in England. He did a lot of work on black holes, theoretical work on black holes. Became very famous, wrote several books. He also has shown up in different TV shows, like he showed up on The Big Bang Theory and several different Star Trek episodes and so on. So, very famous physicist from England. Well, he got the Hawking radiation named after him. And I'm going to tell you how this works, but you got to expand your mind a little bit because this is a little different than anything you've probably ever heard of in your life. But one of the things that they worried about was when the universe formed in the Big Bang, it was possible that you could have what they call these micro black holes. Very, very tiny black holes that were so tiny that we're talking the size of atoms or something like that. But once you create a black hole, then it would start to suck in material and take the material out of our universe. And could those micro black holes still exist? And so that was one of the questions way back, and this was in the 70s, 80s. And so Hawking thought about that, and he realized that, no, there's something that happens that actually gets rid of micro black holes. Stay with me here. So here's our black hole. And we have our event horizon. Remember, inside here, the escape velocity is greater than the speed of light. Outside, it's less than the speed of light. It's less than the speed of light, okay? Now, quantum mechanics and the way we think the universe works is when you get down to that level, things actually work as a probability instead of an actuality. So what can happen is, out of the emptiness of space, two particles can just randomly appear. Like you can get an electron and a positron, which is the antimatter of an electron. Yes, antimatter is a real thing. We use it in CERN colliders and all kinds of weird things. So it exists, and you can create these what they call pairs of particles, and they can pop out of nothingness, out of just the vacuum of space, as long as they pop out and then go back together, and they do all this in what's called a Planck time in about 10 to the minus 43 seconds. And those fluctuations can happen in just random space. And it doesn't affect the physics or anything else because everything that goes away. It's no violation of the conservation of energy or mass or anything like that. And normally that's no problem. But weird things happen when you're close to a black hole. So a black hole, if you have two pairs of particles pop up and one pops up just inside the event horizon, one pops up outside the event horizon, this one could actually escape from the other particles because they can't come back together and recombine and enter into the blankness of space. And so all of a sudden you created a particle out of nothing. Well, you can't do that because then you're violating the energy conservation. You can't make something out of nothing. You have to have the energy to make the object. And so what happens is when this particle is created, that one was lost to the black hole, that particle's mass was created by stealing mass from the black hole. So you've created mass by making the black hole's mass smaller. And they call that Hawking radiation. Now for a big black hole, any normal sized black hole, 3, 4 solar masses up to millions of solar masses, this Hawking radiation is so small it makes almost no significant effect at all on the black hole. Okay? It's kind of the way black holes can evaporate. Think of it that way. But the large black holes, this is really a trivial thing. They gain way more mass than they ever evaporate. The evaporation is so small. The Hawking radiation is very tiny. But when you're talking micro black holes, where the black hole is so tiny anyway that one particle is as big as a black hole, then it's a big effect. And what Hawking showed is that if there were any micro black holes created early in the universe, they'd be through Hawking radiation, they would all along be gone right now, and they're not a threat to us. So, don't have to worry about that. Okay, so that's the background of black holes. Now the question is there any danger from black holes? The truth is, if a black hole came anywhere close or into our solar system, even the smallest black holes, 3 or 4 solar masses across, it would completely disrupt the planets and destroy our solar system and destroy all life on Earth, and the whole solar system would be gone. So yeah, catastrophic completely. Now the problem is, or the reality is there's no black holes close to us. They're not just black holes whipping around and gonna run into us or destroy the solar system. So the odds of this are so tiny that nobody's even been able to really figure out what the odds of something like this would occur. There are black holes around, but chances of ever one coming anywhere close to us to cause any kind of damage, not likely. But it is an interesting scenario. One of the bad things that can happen if you try to fall into a black hole is, let's say you're falling into a small black hole. Here you are falling into the black hole. This is the black hole. The problem with black holes is you got all this gravity, but it's coming from a very small area. And so the pull of gravity on your feet is stronger than the pull of gravity on your head. We call that a tidal force. And that's what makes the tides on the Earth, the water going up and down, is that the moon pulls stronger on the water on one side of the Earth than it does on the other side of the Earth. And because of that, then you get these bulges of water, which creates tides every day. Well, tidals occur even stronger around black holes because all of that mass is concentrated in a very small area. And so what would happen is you would get stretched. Your body would get stretched out in the direction it was falling. You would become spaghettified, or what they call spaghettification. Essentially, it would make you into a long strip of spaghetti. And then, that would not be good. You would be ripped apart. In fact, this would happen very quickly. The force on your feet as you got close would at first be just uncomfortable. Then it would quickly go to about 10,000 times stronger than on your feet than on your head. And that would just rip your body apart. And then even the atoms themselves would get ripped apart because of this tidal force, until your whole body is ripped into its base particles. Protons, neutrons, electrons are all separated from each other and fall into the black hole. Now, you say, oh, but I want to travel to a black hole. Well, there's a way to get around it. If you go to a supermassive black hole, one like we find at the center of the Milky Way, 3 to 4 million solar masses of material. Then, because it's so large, the pull on your head and on your feet is about the same, and it wouldn't cause the spaghettification, and you could fall into that black hole and survive and not get destroyed. So if you're going to go into a black hole, go to a really big one. Now, the closest supermassive one is the center of our Milky Way, which is about 25,000 light years away. We have no way to get there. No fear, though, because it's nowhere close to us and we're orbiting around it. It's kind of like the sun. We're not going to get any closer to it, ever. And we find that these supermassive black holes, we find these at the center of pretty much every single galaxy. Every single large galaxy has these supermassive black holes at the center of it. One of the questions in astronomy now is, did the black holes form first and the galaxy formed around it? Or did the galaxy form, and because of the way the galaxy forms with all the mass in the center, the black hole then migrated to the center and grew there? So we're not sure which came first, the black hole or the galaxy. All right, so best thing to know about black holes is if you're going to fall into one, fall into a really big one. Okay? And yeah, let's talk about the PowerPoint. So I'm going to do that next one on Black Holes Part 5. I'm going to bring up the PowerPoint. We're going to talk more specifics about black holes using pictures and parts of the movie Interstellar. So that's on Black Holes Part 5.